as I was saying, this point of establishing a bijection is quite difficult. So over here in example 7.4, I'm using decimal representation. Now what does the decimal representation use? Of real numbers. It uses a hell lot of structure. What we will see later on, if we can make up to it, it is called a Dedekind complete ordered field. Okay. So this big structure is utilized to its fullest extent to show that every real number has a unique infinite decimal representation. And once we get this, as a corollary to this, we can immediately then settle the issue that the cardinality of the reals is therefore much bigger than the rational numbers. Okay. Now, so you can imagine that it is just not quite yes, schroeder bernstein tells you a lot. It tells you you are only to find two injective functions, one from each side into the other. But finding an injective function again boils down to understanding those sets, and sometimes we would have to understand it. We would need extra structures, extra extra gadgets to be put on that set, and then we can understand it better. So the whole point of view that I want to make is again over here as a particular corollary of this instance. There is nothing called topology, analysis, geometry, algebra, blah blah blah. Everything is mathematics. There's only one thing, and that is mathematics. If we have to understand an object, then there is one kind of structure which are algebraic, another kind of structure which deal with limits, or and you merge these two, you get geometry and so on. But nevertheless, all these are structures, gadgets, which are put upon a set to understand that set much better, in a better way. Okay? So, even if we started with our counting business, we will see that, the way I wrote this is almost to force this point that groups or other structures or limit-like structures, they are not just because one day somebody thought, let us give Charlie, Ayub, Stanley and others a hard time and let us think of such problems. It is because they were necessitated to bring out these structures, to think about them, to understand much more of something which seems to be much simpler. So it is only structures are not there just because it was thought on one day and it came up. It came up because it was necessary for them to have come. So establishing the equality of two cardinalities or the inequality between them is not a trivial question, by the way. It can take some time. So you should not get disheartened, but rather you should take your failures in a positive way, that something is missing. You must know something more about those sets. So that should be the correct thing. Okay, so should we now proceed? Yeah, please carry
Can
on.
I just ask a question?
Yeah.
Would it be reasonable, just thinking about the fact that you've got two sets, one is rational, the other one is real, okay? And so wouldn't it just be common sense that the reals, in terms of cardinality, must be greater than that of the rationals?
Why?
Because the rational set has got some restrictions.
Has some
Restrictions.
kind of?
Can we also take the real set as being a superset to the rationals?
Okay, so here is another example.
That's what I guess is.
But you see, the natural numbers is a superset of the even numbers, right? Right?
Yes, that's true.
But they have the same cardinality. Right? Same again, the integers is much more, is bigger than the natural numbers, but they have the same cardinality. The rationals are more than integers. It's a bigger set. But still they have the same cardinality. So,
Can I come in there?
Yes.
I think I understand what Ayub is trying to say, and for me, who's coming from an engineering background, seems to see things that way. So I need to change my perspective to prove everything rather than saying it's common sense. But if you look at the number line and you put in rationals, there'll be a gap. There'll be gaps in your number line. So you will see that something is missing. So,
would you really see a gap?
I'm not trying to say it's going to be a proof. We need to prove it so that anybody can agree that that's what it is, rather than intuition telling us to be that way.
Okay, good. That was a good argument. But let me tell you over here that there is a much longer story. So, what do you mean by a gap? So, let's see. So, this is in fact how Dedekind started with this procedure. So, you see, what Dedekind started was he called constructible numbers. Now, constructible numbers, what are they? Well, the idea is like this. How do you plot the number line? So first on the line, so you have a line, you fix a, oh sorry, I didn't start sharing my screen, right? So you can see my screen now.
Yes.
Okay, so you have a line. Now you fix a point which you say is your zero or your origin, and you fix a direction, you call it the positive direction, and you fix on one more thing, which is the unit length. Okay, so you fix two things. So the unit length, you say that this is your unit, so this is 1. Now how do you, so what is this description of a constructible number? X is a constructible number if is a constructible number if you can produce a geometrical construction using rulers and compasses only, for the length. Compass is only of a segment of length x, say. So, the starting point 1 is a constructible number because you have produced, you say that x is a constructible apart from 0 and 1, that's the definition you give. So, obviously, if you can produce a length x, then using your, so you will place your compass here and then you will have a construction of the length of minus x. So immediately it follows from this that if x is constructible, so is constructible, then so is minus x. Okay? Then you obviously find if xy is constructible, then x plus y is constructible also. That's also trivial because you can copy a length, right, using ruler and compasses. And you know that if x is constructible, then similarity constructions and triangles tell you x by y is constructible. If x is constructible, again similarity constructions tell you, then, and x is not equal to 0, then 1 upon x is constructible. So you can add, multiply, divide and so on. Okay? Now, and Dedekind then said, okay, he was very happy because he found many. So he found from here that all rational numbers are constructible. Not only rational numbers, obviously he got from here square root of 2 is constructible, square root of 3 is constructible. For each natural number n, he found a construction for square root of n. Pythagoras theorem gives me this. Okay, so there are some irrational numbers, they are fractions and so on and so forth. So therefore all surds, so things like this, a plus b root p, a and b are constructible, that's also constructible. Okay, so if x is constructible, so is square root of x constructible. Again the same thing, circle constructions give you this and so on. That's fine, that's fine. So then he said that he came upon this conclusion, therefore, that all the points on this line correspond. In fact, his original naming was not constructible numbers. He gave the name real numbers to them. But later on, it was found that they are not definitely all the real numbers. And there comes a big gap, almost 200 years, and someone proves that x is constructible. If and only if it is a solution of a polynomial with integer coefficients and degree 2 to the power n. And these are, so therefore, as a result, as a conclusion to this, people showed that the trisection of an angle is not possible by ruler and compasses, because cos 60, for instance, cos of 30 is not constructed. Okay, sorry, I made a mistake. Cos of 30, no, not cos of 30, it's cos of half of 45. What is it? 22 and a half. Is not constructed. No. Why? I said trisection. Yeah. So cos of 20 is not constructible number. That's how it was shown that 60 degree cannot be trisected even. Okay. So what are these numbers then? Well, they are today they are called algebraic. They are called special kind of. They are in fact called constructible numbers today. So you see, we started off with natural numbers. It's bigger than integers. It's bigger than cube. It's bigger than constructible numbers. It is bigger than something called real algebraic numbers. Well, what are they? They are nothing else but the roots of polynomials in a single variable, obviously, with integer coefficients. And then comes your reals. And up to this, all of them have the same cardinality. Cardinality same. They have the same cardinality as n. So now if you are thinking of gaps, of producing gaps, you see via constructions, so via geometric constructions, you cannot even find these gaps. Okay? You cannot even find these gaps. So although, yes, Stanley, you are right, you have to think somehow else, but then it was seen that that was the most natural thing to think of, and it turned out that the reals is even more mysterious than trying to so it is something which is much beyond this construction process. Okay, so
sorry, Don.
Yeah.
Can we then conclude that the irrational numbers would be in this construction set?
Not all irrational numbers. Some are. So, for instance, E. I have already given. Cos 20 is not constructible, so it's an irrational number which doesn't have a construction. There are many other numbers, E, pi, and so on, things that we know. So they don't have a construction. Often they are often called transcendental numbers. Transcendental numbers. With the idea of trying to convey this, that it transcends the process of all these constructions. Yeah. So there exists no such construction using ruler and compass for this. By the way, since I said about ruler and compass, I must also say that Euclid's ruler is just a straight edge. It doesn't have any marks. Okay? And Euclid's compass is if you look at our compasses, it looks like this, and there is a screw over here, right, which tightens it. Now Euclid's compass doesn't have this screw, so it is just this. So the moment you can put it at one point and draw a circle like this, but the moment you take it up, it collapses. So it is often called forgetful compass. It forgets the length. But then Euclid, using his methods, he tells us that there are 5 or 6 initial geometric constructions by which he guarantees that you can copy, so you can tighten the screw of the Euclid's compass, and you can have a marked ruler, so you can make marks on it. So that's why we use marked rulers and compasses with screws, but originally Euclid's definition of compass and ruler doesn't have this. And fortunately enough, I must say, we had a teacher who was whose screws were equally loose. So when we were kids and learned geometric constructions, he used to come with a screwdriver in his pocket. He used to take out our compasses, compass.
Compass.
Yes, and loosen its screws and write a note in the geometry box to our parents not to tighten it. And he replaced each one of our rulers by a straight edge which did not have any marks. And until he did all those 9 constructions and made us understand that even with this I can make a straight edge with marks, and I can copy a circle of a given radius from one place to another. That means I can tighten the screw. And then he allowed the screw to be tightened. So we understood it much younger that what rulers and compasses were, and this Euclidean construction. And it's a fascinating area. There is a beautiful book, Geometrical Constructions Using Rulers and Compasses Only. You can have a look into it. It tells about this story. It's a very nicely written book, Geometrical Constructions Using Rulers and Compasses Only. And it's a Russian monograph, translated in English, Mir Publications, and that's the first part. The second part is geometrical constructions using compasses only, and geometrical constructions using rulers only, and they are all equivalent. With compasses only. With rulers only is a subset, but with if you bring in compasses, so rulers is actually not required. Whatever you can draw with rulers and compass, you can draw with the compass only. But with rulers you don't have that. You come, and this is exactly what you do in coordinate geometry. With rulers and compasses you can. That means with rulers what you can do is only straight lines, so intersections of straight lines and straight lines. But the moment you bring in compasses, you can draw circles, and therefore you can draw points which are intersections of circles or circles and straight lines and so on. So therefore you can have more and more points. So that is the whole idea of this monograph. It would be nice if you could read it. So, and it also deals with this transcendental feature. It's a very nice Russian. I think it was written by Uspensky, if I am not wrong, or I have forgotten it. Uspensky, Mir Publishers. Mir Publishers. It's a Russian. Possibly.
So, Doctor,
Yes?
would the Euclid compass be a fix?
That's what I was
At this
saying.
point,
That's what I was saying. That Euclid's compass,
the wonderful bit.
as he defined it, as he defines it, is not fixed. So the moment you pick it up, it forgets that distance. Right? So it's a contractible compass or a forgetful compass. And the rulers don't have any marks. It's just a straight edge. Right? But then one of his first tasks after defining this is to show that he can copy a line segment drawn at one place. So if he draws a line segment of a given length here, then he can copy, means he can draw another line segment of the same length at another place. Okay, so that is his first thing. And the next thing that he does is, suppose he has a circle of a given radius with a given center, then he can copy that circle. So that means he can draw another circle of the same radius but having another center. So if he can do these two constructions using his unmarked ruler and contractible compass, what it means therefore is he can remember the radius and he can use marks on the rulers, because he will use these marks, and therefore he now uses a marked ruler and fixed or compasses that do not forget, so non-contractible compasses which do not contract. Okay, so that's how Euclid proceeds. So you see, there is the whole story is much more involved. But you're right. It's just not the intuition. So cardinality. So one thing therefore comes up. One way of sensing some set is bigger or smaller is obviously via injection or via subset and so on, which is injection. But this notion of being a subset doesn't actually tell us whether there are really or significantly more elements or not. So, because n is a subset of Z, but just as sets, Z doesn't have significantly many more elements than n does. Well, we need some more structure to say, no, Z is completely different from n. But that when we say, and that somehow is fixed in our mind, which is playing the trouble, which is playing the nuisance over here. Yeah, remember, whenever we are thinking about a set, we have stripped off all its other properties. Only the specific property of being an integer is there, nothing else. And this business only tells us that if we do not consider anything else, then there are no significantly many more integers than natural numbers. Okay? There are no significantly more rational numbers than, so it's the same thing, it's the same set, essentially. They are in bijective correspondence. But the moment we start thinking of an addition, so addition is an additional structure, and we know under our usual addition of numbers, we cannot invert naturals, and that's why we have z. So it is different. We cannot have multiplicative inverses of integers, and that's how rationals came in, and so on and so forth, all this story. But remember, at each stage, therefore, we are bringing in more and more structure to make the difference. Not as sets. As sets, as I indicated, up to real algebraic numbers, they are all having the same number of elements. So it would be very, very difficult to distinguish these sets, to say how they are different. I mean to say, yes, you will say, well, one is an integer and the other is a natural number. It is by property they are different. I said, yes, you're right. But what of that property? Now if you start thinking, what of that property, then comes more and more into the story. Right? So just as sets, these sets, as I have written, they cannot be distinguished. So we need more and more structure to understand that no, they are different as sets. They are not the same. So to understand, so you see, to understand more of Z, you need more of structure. Okay? So, yeah.
A question, Doc.
Yeah.
I've seen there you said square root of 2 or square root of n, even if it's a prime, is constructible.
Yes.
And you say an irrational number.
Yes.
But the transcendental numbers are not constructible.
No, they are not. Yes.
So the transcendental numbers are not irrational numbers.
They are
These irrational numbers?
They are irrational numbers, but they are a subclass. So if you look into this be the set of all real numbers, so here is your naturals, then you have a bigger set, so I mean this side, so this bigger one, including naturals, and so on, you come up to rationals, and the rest is irrationals. Now, amidst these irrationals, there are some numbers which are constructible. Then there are some others which are real algebraic numbers. And then the rest of it are called transcendental numbers. And this part is usually in short called the irrational numbers. The irrational numbers. Okay? So things which are not rational are called irrational numbers, but irrational numbers are of certain kinds. One, there are irrational numbers which are constructible. There are irrational numbers which are real algebraic but still not constructible. Okay, so for instance, here is an example of such a number which is real algebraic. It satisfies a polynomial equation with integer coefficients, but it doesn't satisfy. So you might be interested to see what is it. Well, this is where your half angles and other angle things come into the picture. So you know cos of you know this cos of 3 theta. This is cos 2 theta cos theta minus sine 2 theta sine theta. Now this is 2 cos squared theta minus 1 times cos theta minus 2 sine squared theta cos theta. So this is cos theta, right? Because this is 2 sine theta cos theta multiplied because this sine theta would become this. And then you see that this is your 2 cos cube theta minus 2 cos theta from here, and this is minus 2 cos theta, so minus 4 cos theta plus this is again a plus 2 cos. So this is again a 4 am I right? Sorry, this is 2 cos squared theta and this one, and this is a 4 cos cube theta minus 3 cos theta. So this is cos 3 theta. So therefore cos 60 you know is half. This is 4 cos cube 20 minus 3 cos 20. So therefore if you have this equation 8x cubed minus 6x minus 1, this polynomial cos cube, so cos 20 is a root of it. Okay, but this is not of the type, its power is not 2 to the power n, and hence it's not constructible. But this is still algebraic because it's a root of a polynomial with integer coefficients. So it's algebraic, but it's not constructible. Yeah. So you see there are, and then you have things like e and pi, which so the fact that, for instance, e is there cannot exist. So this is a very, very deep theorem. Theorem in real analysis, in fact, there cannot exist a polynomial with integer coefficients whose root is e or pi, e or pi. So this is a very, very deep theorem. It requires quite a bit of real analysis to prove this theorem. So therefore there are numbers which are not real numbers which are like this, and it therefore says that and then again obviously I must say that this part is also kind of segregated into or divided into several layers, but that's much more deeper. It's segregated into much layers. It's by degrees of transcendence and so on, and so, but that's much more deeper. So that's how the real line looks like, the set of real numbers looks like. But you see, to do all of this, you would require a hell lot of structures, just not 6. So you need more and more and more structures to establish this beautiful picture. And more structures explain it, the more clearer things become. Okay? On that issue I'll stop here, but yeah, if you have any questions. Any questions?
Maybe lastly, for me, not to extend the question, those three sections of irrational numbers,
Yes.
do they have the same cardinality?
Yes.
Like the transcendentals and the constructing and the...
Yeah. No. The constructible numbers are still countable. The real countable means it has the same cardinality as natural numbers. Real algebraic numbers are also countable. They have the same. So I didn't carry on with that countability business. So let me just say over here, I just paused with my notion of cardinality just here because I wanted to let this settle down for a little bit. But since it came up, so the definition let me provide. A set X is said to be a finite if there exists if X is empty or there exists a natural number n. Now you will say, why is this? Then this can be such that X has the same cardinality as this. So that means there exists a bijection between these sets, these two sets. It is said to be finite. That's the definition of a finite. Infinite if it is not finite. And it is said to be countable or countably infinite if so something which is either countably infinite or finite is called countable. Okay, so you see, this is trying to say cardinality wise. So we start off with the empty set, then we have this one element set, then we have, so this is how we will in fact build our natural numbers also. This we will often call the zero, but I'll still write this as this. And then we have 3. So let me write this as 2 union 2. So this is often called the successor of, and so on. So n is n minus 1 union. So it's a loose way of writing, right? But obviously I have assumed such things. And then suddenly you carry on and on and on, and these are all finite sets, and then you have the first infinite set. That's your natural numbers. Now at this level there are several sets which are in bijective correspondence with this. Several things. So for instance, this, whereas over here this is strictly in terms of cardinalities, right? So I write a comma to say, to emphasize that no two of these are in bijective correspondence, but here there are many which are in bijective correspondence. Z, n cross n, as we saw last time, q, q cross q, and so on. And there will be another big thing which we will do later on, is suppose if each AI is countable for I in I, and so also is I. Okay? So this says that their union is also countable. So it kind of says a countable union of countable sets is countable. So this phrase says a countable union of countable sets is countable. Okay? So there is no way you can go out, it seems. But then the first time you come out of it is, we already know by taking the power set. Now, whether this is the first time or not, first time uncountable, this is a big question, but we can see that, we can easily see, and that's what I have proved also. I have shown that this is in bijective correspondence with the real numbers, with complex numbers, with R cross R. Why R cross R? R to the power n, where n is any finite, right? And so on. And why this even? Even if you take sequences of rationals. Okay, so that's there. But whether, so when do we exceed this? Well, we can exceed this by taking, so you take unions of, again, the general principle we will show later on is a small, if we say something like this, will again, so if AIs are sets whose cardinality is at most this, less than or equal to this, and I is a set, the indexing set has cardinality less than that, then their union is also cardinality less than this. So we will have this principle, a small union of small sets is small. This is always true. Whenever you understand smallness to be having at most a number of elements given cardinality, right? So we will see such theorems getting true, okay, such facts. When do we exceed it? Well, you take again the power set. And there will be many others, and this carries on and on and on. This gradation carries on and on and on. The question remains whether there is any cardinal number, any set. Today we will not possibly proceed with our notes, but it's interesting to listen about these things or even learn about such things. You will take possibly years, but it's nice to know. So I'll tell you this story. So whether there is any number, any cardinal number between n and 2 to the power n. So Cantor said there is none. So Cantor's hypothesis is this. It's often called CH. It says that the first uncountable cardinal is this one, is the cardinality of this. That's what Cantor said. He thought this was right. But in 1960s, I should also say that things like this went on. So 2 to the power n, and then the next one is 2 to the power n. The absence of anything in between and all such things, they are usually called generalized continuum hypothesis. This is actually Cantor's. This C is for continuum hypothesis. Continuum means, yes, you understand what I am trying to say, that n and just after that is 2 to the power n, just after that is 2 to the power n, just after that is makes its power set, and so on and on. So saying that there is nothing in between these levels is what is known as generalized continuum hypothesis, and only for this level is known as Cantor's continuum hypothesis. Why hypothesis? Well, this was belief pre-1960. But strangely, using a technique which is called forcing. Now, what is the idea? The idea is the following. When you are going to say about all of this, and that is actually the second part of my lectures, I don't know, of the notes that I am writing, which will give you the set of axioms. So the moment you start off with a set of axioms, the questions is that, okay, you have assumed those axioms and that is your set theory. So naturally someone will try to prove, either he will assume this axiom, this hypothesis, or if he doesn't, he will try to prove it. Now, if you can prove something, if it was possible to prove this continuum hypothesis from those axioms, we would not be much elated. We would say it's a consequence of those axioms. But if you can show, till the time you cannot produce a proof, you have a question, you have a doubt whether it is true or whether or not. What Paul Cohen did was beautiful. he exhibited two examples. In one example, all the axioms that have been chosen of sets is true, and yet in that example, so he produced two examples. In example 1, all the axioms of set theory holds, plus the continuum hypothesis holds. And in example 2, all the axioms plus the negation of, plus the fact that the continuum hypothesis is false. This holds. What does this mean? That means he produced in this second example, he produced an example of a set X. So in this example, he produced a set X such that it has a one-to-one map from n to x, so injection from here, and an injection from here to this, but there is no injection the other way around. So that means in this example he could produce a cardinal number in between that of n and 2 to the power n. So this fact, the cardinality of this x therefore is uncountable, and this one therefore it is smaller than 2 to the power n, therefore suggesting that 2 to the power n is not the first uncountable cardinal. Okay, so he produced two examples, and the method by which he produced it was later came to be known as forcing. See, he forced the production of a generic technique he produced there to produce such counter examples. Okay, it's a tremendous revolutionary paper where he did this. So what does this mean? It means that the notion of continuum hypothesis is independent from the notion of set theory given by these axioms. What does this therefore mean? It means it depends upon you as an user whether you would accept continuum hypothesis or you would not accept continuum hypothesis. Or as an user, whether you would like to say, if the continuum hypothesis was true, that means you work in models or in examples like example 1, then certain things are true. And if the continuum hypothesis is false, then certain things are true. Okay? So it changed the way mathematicians started thinking about sets. Even sets are not, they are not even engraved in nature. So it depends on those axioms, right, which you have taken for them, and thereby it depends what kind of sets. So now you see, even accepting your Boolean, classical, logic and blah blah blah, not even going that far, there can be several worlds of sets. It depends on which one you are going to accept. Okay, so there is no one unique world. For many things there is, but there is no one unique world for everything to discuss. So as you can see, this itself, this whole idea of producing a one-to-one map and so on, these are very, very deep questions. So, as I said last time, we are now starting to enter deep waters. Yeah, it's just not union, intersection, complementation, and blah blah blah. Yeah. With that, I will stop. Possibly, okay. We did not do any further sections, but I believe this exposure to current literature is also necessary. Yeah. Now, for your questions, your queries, and so on. Am I lost? Have I lost all of you?
Nope.
We are still with you, Doc.
Okay.
Yeah, we are still with you.
So, Doc, for next week we should read section 8.
Okay, all right. And Charles, we'll come back to it next time. But yes, before we finish, because I still have to answer what Charles asked, and I'll do that in 5 or 10 minutes. But any other questions on what I have said so far? So you see, it's a big thing now, this notion of yeah. Okay, so I'll just highlight what Charles was trying to ask. You see, if you have a relation R, which is an equivalence relation on a set X, so we have already seen that this partitions and the set into subsets, right? In a sense that any two elements within this subset are equivalent. So if you take x and x prime, so x prime is related. So this is an equivalence relation. But if you take y, x is not related with y. And we will denote by this symbol the equivalence class of x. Yeah, I think we introduced this symbol also. So you see, this is a subset of x. And as you vary, now a little bit of an understanding, as I said, see, the idea is that we would, so remember that exercise where we took this square sheet and we said that we would identify this edge. So that means each point over here gets identified with the corresponding point over here, right? So, and the resulting picture was that of a cylinder, right? Right? So that was this. Then we can identify this side and this side, and you would get a tire or a torus and so on. So you see, so that was, now if you look into what we are doing in general, So it means that all these elements are punched into one. All these elements are punched into one. And that's how I am taking this new set whose elements are x by r. So this set y by r, and so why I wrote this y by r is to indicate that these are all the elements which are r equivalent to x. Okay, so as if say r glued to x, glued by this rule suggested by r to this element x, and that's how we get it. Now observe, when we come to this set, remember we cannot go any more further inside a point, right? So this is a point, this is an element of this set, and this set was denoted by this way, capital X by R, saying that this is what we get when we glue in this pattern, right? So just as an example, this was the original set X, all right? The relation was identify or equivalence relation was this. So the partition was suggested, this and this are in the same partition. Similarly, and points on the plane, they are all singletons, right? So that was the partition suggested. And we knew that partitions and equivalence relations are one and the same thing. And then when we glued these two, so this is my set now x upon r. Okay, so its picture has changed. Okay, so that's the notation. And then there was this nice map which was called the factor map, that is a surjection. As we agreed, we would denote surjections by this. What was it doing? It was taking x to its equivalence class. Okay? So that's basically the symbolism which is adopted in this section on 8. Okay? So try it again. Charles, does this clarify a little bit at least?
Yeah, I'll sit down and try to glue the facts together and see whether I'll come up with something.
Okay. All right.
Yes. Thank you very much.
So next week we will look into section 8, that is kernel pairs. So we looked into a little bit of this injection business, which is essentially to do with counting. Let's look into the other side of the story, which is killing or gluing and so on. And we will then show a beautiful relationship between those two, saying roughly giving this philosophical picture that whatever you can do by this building, that is coalescing and joining and injections and so on, you can do the same thing almost by deconstructing. So by taking equivalence relations. So there is a nice duality. One side is constructing, the other side is breaking or destructing or killing, and you get the same information from both the sides. So there is a nice duality, there is a nice connection between these two. So we will see this next time. So giving this philosophical picture. Yeah. So with that I'll stop here, but yeah, you ask your questions, and next time we'll look into section 8.
Sorry, doctor.
Yeah.
How how do we link the concept of the name to these equivalence classes?
The name,
There was like, you call it a name function or something like that.
the name function. The name function, was it not given to, so if x was the set and x was an element, small x was an element, by the name of x was denoted the function x from the singleton to x, which takes this to x, right?
Yes.
And then if we look into the set of all functions from 1 to x, they are then, and so the name produces a bijection, right? This produces a bijection between these two sets. So it says that there are, so therefore, yes, this also says, it says that there are, and not only this was not only a bijection, but this was much more. It was actually a natural bijection. So if you have another set y and its name, so if we say this is the naming procedure for x, so to highlight that, let me say, how do I write it? Say I put a, okay, somewhere let me put an x like this, or to say that this is the naming procedure for x. Now you have therefore the other bijection also, which is the naming procedure for y. Okay, and if you had a function, then, well, this is the composition. So what is it? You take x, you saw this, you take x, you take it to the name. So this is a function. Now this is a function from 1 to x, so you compose, so this is actually nothing else but the composition. So you compose with this, and on the other hand you take this f and it takes you to fx, and you have the name of, so this actually takes you by this naming over here to the name of the name function for the element fx, and these two were same. So you had this equation, the name of fx is same as f, the image of the name of x. So that's how we realize this. So it says therefore two things. One, there are two ways of looking into elements. One is what we usually do explicitly as considering them as elements, or the other one is looking upon them as functions from the terminal set or from the 1 point set to x, right? So there are, and how to look at it? It is consider the name function. So the process of naming is just a labeling, it's just a relabeling your elements as functions. So that's what naming is about. Okay? And naming, so this equation therefore tells that naming is invariant under change of sets by functions. In what sense? The name of the image is image of the name. See, you can read it in this way. the name of the image, fx is the image of x, right? So the name of the, so you can even write it in this way, name of the image obviously you meant of, name of the image of an element, right, is equal to, is the image of the name, right? So that's what it says, right? So that's how we can get hold of this mnemonic of this equation. It says that the name of the image is image of the name. So the name is preserved under change of the set by if. So it is something natural. It is not this bijection between this renaming of elements as functions from the terminal set is not something special of a particular set. It happens likewise for every set X. Okay? So that's the idea behind naming. Yeah? And
Thank you, Doc.
okay. This idea, the naturality, rests here. So naturality is just like saying, well, here is an example of a bijection or of a function. And when you say that this is natural, it means likewise. So that means I exhibit a thing for a particular set, and you can do the same thing likewise in the similar way, in the same fashion for any other set that you might take. Yeah? So that this likewise business is all about this notion of naturality. Okay. You see, as teachers, I don't know whether you are involved in this teaching, in this process of teaching business or not. I mean to say this teaching profession or not. So that is whether you are yourselves teachers or not. But definitely you have heard your teachers say, likewise, do it likewise, right? So it's exactly the same thing that I'm saying. Likewise. And that's precisely the meaning of naturality. Likewise, it can be done. This what I have done, what I have exhibited is only for a particular case. But you can do the same thing for any set, any other instance of that, of a set. So likewise you can do it. So that's what is meant by naturality. Yeah. Anything more? Yeah?
Good, Doc.
Yeah? Anything more?
Not from me, Doc, thanks.
Thank you.
Yeah, even master.
Okay. Okay, then we meet next time with section 8. And then so keep well.
Okay.
Thank you very much, Doc. Keep well, Doc.
Keep well.
Thank you.
Thank you.
Bye, everyone.
Bye.
Thank you. Bye.
Thank you, Dr. Parsal.
Thank you. Thank you. Bye.
And everyone else, goodbye.
Bye, Ayub.
Bye-bye. Charles.
Okay.
এটা তো বিশ্বাসই করতে